One is smoking. One is what?
Come on, guys. Come on.
One is smoking, one is eating, one is cigarette.
What the heck?
What's going on? Yeah, I'll do that first.
0.
Steal the apple back.
Is it his apple? Is it?
Oh my.
Whoa.
Oh. Can you give the apple back to the child, please, Monica?
I'm not a child. Okay.
You're a child.
I'm a child. I'm a bone.
You're 7 years younger than me.
Baby.
I'm a boy.
This class is so strange. Okay. Continuing, guys. Guys, continuing. Bruce, we'll continue.
Okay.
So, before we start the next lesson, there was a question from the last lesson.
Yeah.
Which one is that? Now? Y equals... yeah. 5... I think once you get the idea from this one, you'll be able to try the next one. Right, so I asked you for the derivative here, and I gave you a little hint. Use implicit derivatives.
What is it?
Yeah. Any ideas on what I could do first?
Make it equal.
In other words, what's the problem here? Why could you not get a derivative?
Yes, we had x minus 1.
The y, usually when we're using implicit differentiation.
No. Why can't you differentiate 5 power x?
Because there has no followed by 5. Oh,
Yeah, it's not x power 5.
Yeah.
It's 5 power x. So the problem is the x is in the power, which it normally is not. So how can we take something out of the power?
Log.
Yeah. So log y equals x
Log 5.
log 5. What's the derivative here?
1 over x.
dy dx. Wow.
What's the...
Log 5 plus x.
Just log 5.
But plus.
Just log 5.
Just log 5. Because this is the same thing as a number by x. What's the derivative of 2x? 2.
Wow.
What's the derivative of number x? Number. Yeah. So what's the derivative here? It is y log 5. But what is y? That's the answer. That's the answer. Okay, write this down, Saul. Write this down.
Okay.
Sine. I want you to try sine and then I'll do it. Yeah, sine inverse. No, but now that you've seen this one,
what's that?
let's review. If you look at the y equals if you look at the y equals sine inverse, what is the problem with that is making it difficult?
Inverse.
So how can, a bit like what we did here, we cancelled the power problem out. How would you cancel the sine inverse problem out?
Times 5. What's the question, sir?
What's the derivative?
No, I mean y equals.
What sine inverse x? Once you've written that down, try to do something similar for this one, please. What's the derivative here? Just plug this in.
Equal 1?
Y equals 1. The answer? No, no. You have an answer, Lee, for this next one?
No. Wait.
Okay.
We need product
You need the product rule for this one?
What, you done? Y sine x.
Yeah, we should.
No.
What?
Why do you have sine x?
Because I times sine x and both.
Well, not sine x, just sine.
Can we times this sine?
Yeah, I thought what you meant was put sine on both sides. I didn't correct you when you said times. I didn't realize you really meant multiply. You need to apply a sine to both sides. So the next step would be to do this. Yeah, well, what is sine of sine inverse?
X. Maybe sine X.
What?
Just x.
Mm-hmm.
Just x. Yeah? Okay, what do we do next? What's next?
What is that sine?
Huh?
Sine X.
On the left?
Yeah.
No, sine y.
Sine what?
What I did was,
Oh,
I put a sine here and a sine here. So now I have sine y equals x.
Yes.
No?
Just sine y.
Well, I'm not finished. People are confused by the first step. What's confusing you? I sense confusion here. What's... Well, I haven't even started yet. Can I continue? This isn't finished. Yeah. Yeah, so I can continue to get... Yes, yeah. So, what should I do next? Derivative.
Yeah.
So, what's the derivative of sine y?
Cosine y di
Cos y
dy over dx.
equals
1.
1. So, what does dy dx equal? 1 over cos y. Well, yeah, what is y equal to? Cos sine inverse x.
Yeah.
Now, I gave you problems like this in semester 1. How do you simplify cos sine inverse x, or rather x over 1? Well, you draw a triangle. Opposite is x, hypotenuse is 1, and adjacent is root 1 minus x squared.
Yeah.
If you want the cos, then that will be 1 over, and the cos is root 1 minus x squared over 1. So the answer is 1 over root 1 minus x squared.
Huh?
What's the sine inverse of?
What's the sine inverse of? If cos of sine inverse becomes cos of this, basically, and cos of this is, according to this triangle, root 1 minus x squared over 1 is what it would equal. Because this is the angle here.
Simon, can we substitute sine x equals u?
Cosine.
I don't think it'll help.
Huh?
Y?
Well,
Y equals 1 over u.
why are you getting 1 over u?
Substitute x.
No.
Y.
This is not this.
Why?
Because it's not. because this represents the inverse of the sine, the reverse sine. This does not mean 1 over sine. This means 1 over sine.
Then
This means arc sine, sine reverse, sine inverse,
Sine, yeah.
backward sine, you know. It does not mean 1 over sine.
Teacher, for the previous question, y equals 5 power x, what if you think of like y equals 5 times x times, so it's always 0, right?
No. There's actually another way to do the last one. I'll just show you. If you have y equals 5 power x, you can change that into e log 5 power x, because e and log cancel. You can change this into e x log 5, or rather e log 5x. This is like ekx. The derivative of ekx is basically the log 5 comes down in front, and you're left with e log 5x. But you can reverse the process on the one on the right, so you can go back to saying it's e log 5, and the x can go back up, and then the e and the log can cancel, and you're back with log 5 times 5 power x. So you can arrive at the result using the rules of logs and powers. So you actually have two methods to differentiate this. There's actually another way as well. If you want to go nuts, there's a third method, Lee. You have y equals 5 power x. You could say log y equals x log 5. So you can say x equals 1 over log 5 log y. And if you just imagine the x and y having opposite roles, you can say dx dy equals 1 over log 5 1 over y. So then you get dy dx equals log 5y, which equals log 5 times 5 power x. So I've just shown you 3 ways to do this one now. You want 4? Yeah. Correct. This has come up in the exam twice recently.
Wow.
I mean, do we have to try the cosine to the
No, I've just shown you there's 3 different ways to do this. In the exam they will not specify a method.
No, I mean the other one. The sine.
Yeah, what about it?
Do we have to change that to the root one?
Oh yes. Oh, you couldn't leave it like this.
I cannot.
Well, you know, it depends on the question. If the question said, what's the derivative, then technically this is the derivative and that's fine. But usually this question comes up in the exam as a show. The question would say something like, show that the derivative of this is that. It is sometimes easier to know what you're trying to reach in it. Okay, let's continue now. We're going to the next lesson. These were good examples. These are exam ones. I've seen the power one and the sine inverse one 2 or 3 times in the last 5 years. So I'd say you've got a 50-50 chance of a question like this in the exam. Okay, next now. So we'll take a small break from calculus, and we're going to a new chapter called mappings.
The whole crack.
Yeah, so we're on to this one now. Mappings and functions is our new chapter. Let me just see here. New chapter.
Oh.
Okay, continue. Does anybody know, maybe we should close the windows now that they're blowing hard. Does anyone know this word mappings?
No.
Yeah, you know it. What would you describe it as?
Like on a map,
No.
Walking?
describing the location of a place.
No.
I mean, is it A or O?
Oh, A.
Mostly.
Mapping, yeah.
Yeah, that's good.
I don't know.
Drawing
And the map.
A mapping
Map, oui.
takes
And the map. Map.
Movie.
a mapping takes an element from one set and returns an element from another.
Huh?
So what I mean is you have a set with numbers in it, and you have another set with numbers in it, and a mapping takes one from this and gives you a different or the same element from another. Huh? No, it's not that, I'll give you, like, here's a very, very simple example. Here's the set of the numbers 1, 2, 3, 4, and here's the set of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? A mapping might take 1 and map it to 1. It might take 2 and map it to 4. It might take 3 and map it to 9. Etc. Can you actually see what this mapping is doing? What's it doing? It's squaring. It's squaring, yeah. So where would 4 go to?
16.
It would go to 16, for example. So a mapping, you know, we say it maps. It takes from one element to another in another set. Huh? Like a pattern, yeah, like a rule, a procedure. This is a mapping. So we need to introduce some vocabulary. So just a little bit of notation. Let's just say this, we call this mapping F, no surprise. When we write this, what we're saying is F maps from set A to set B. It is like a transfer, yeah. It takes an element from A and matches it with an element in B. So the simple example of a mapping here is fx equals x squared. Yeah, it takes real numbers and gives me real numbers.
Yeah.
This is what you might call the squaring mapping, as an example. Okay, but these sets have names which we'll get to in a moment, but you might need to write something down here, so please make what notes you need to, and we'll have a look at the key idea for the lesson. Is this something you've studied before? No? Yeah. We're developing our theory on how functions behave. So before we can develop a theory on it, we need the right language to describe it. Another. Continue? Yeah? Well, can I scroll down a little bit? Okay, so you probably know the name of this lesson is domain and range, and that's the two concepts we're going to have a look at. So, does anybody know the meaning of this word here, domain?
The alpha.
No. Getting close, yeah. So what could that mean in this context? The set, which set? The first one, yeah. In other words, domain is the set of values of x that the mapping F can take. In other words, the way I put it simply is it's the allowed x values. Here's a very simple example. If I have this mapping, the domain is not all the real numbers. Why not? Well, you can't put minus in here. What actually is the domain of this mapping? All positive. More than? Could it equal 0? Yeah, so it'd be from 0 to above, yeah, infinity. This is actually the domain here. Yeah. So it's what I call the allowed, the legal values of x. Yeah. Do you understand what I mean when I say allowed? Like the permitted values, the legal values. You don't? No problem. Can you do this? No. Can you do this? Yeah. Yes. So the domain is just what values you can use. So here, for example, you can use only positive, or you could use 0, but you can't use negative. So negative is not in the domain. Only the positive and 0 is in the domain. Domain is what you can use. It's what's allowed.
Oh,
Yeah.
not the whole set.
It's the whole set of everything you can use, which may sometimes be all real numbers, or may not be. But it is only the set of the values of the real numbers you can use. Here's another example. Here's another one to practice on. What is the domain of this mapping?
Not equal to.
Yeah. So the domain is all real numbers except 0.
Exactly.
It's like this, yeah. Okay. What about this function, this mapping? What's the domain here? What's the domain?
More than 0.
Yep. Includes 0?
No.
So the domain is this.
Is that not include 0?
Yeah, not include 0.
So it is like that.
Include 0. Yeah.
Teacher, domain for I or for I?
The domain is for the f. So you would say the domain of f is maybe this.
Domain for x. It's an x number.
The domain is an x number. It's the set of x numbers. It's all the x numbers together. Yeah.
So teacher, this is equal to 0 and
You know what this means when I write it? It means all the numbers from 0 to infinity. I'm sure I showed you this in semester 1. When we did the... Yes, I did. When we did the inequality lesson.
Even with the bracket.
That's if you want to include... That's it's closed. Remember open and closed?
Yeah.
This one is open. Because I do not want to include the 0. And this one here is closed. At the left. Yeah.
Why is the first one not real number?
This one? No, this is.
No. Yeah, you're right.
Oh, no, the domain is definitely not all real numbers because we could not put
Less than 0.
Yeah, we can't use less than 0 here.
In natural,
Yeah.
we have I.
Yeah, we have I, which we don't study. Yeah. Continue?
Yeah.
Yeah. Okay, so let's have one that look a little bit harder. Like for example, here, what's the domain of this function?
Oh.
How could we get this?
5 and 6.
Yeah, I think you all see it. Yeah, this has to be more than
0.
0. So it means x must be more than 6 over 5.
Yeah.
So the domain is this. like this.
Called.
This?
No.
This?
You're right.
This?
Yeah.
What's this called?
Yeah.
What is it? Infinity.
I like the car.
Infinite.
Car. That's
We should pay for that.
Plus.
Plus infinity.
Yeah, plus infinity, yeah. Okay, so what about, let me give you this one to try. What's the domain here? Let's call this one G just to stop using F all the time. Okay, here's one for you to try now. Try this one for me. Give me the domain here. Yeah, give the other students a chance, Jerry.
Okay.
No, it can be 0.
It can be.
Of course, because square root of 0 is fine.
Yeah.
You got an answer? What did you get?
Less than 2, more than 3.
That sounds... Well, hang on, it sounds right. You said x less than 2, x more than 3.
Less or equal to
2, yeah.
Close.
Close, yeah. Did you not get it?
Yeah.
What is the problem here? The problem is we require the square root to take only positives or 0. In other words, for the domain to be found, we need to ask ourselves, when will this be positive? Because we need this to be positive for it to be valid. Yeah?
Or equal.
Or equal, thank you, or equal. So that means x minus 2, x minus 3 must be this.
Yeah.
Quick picture. 2, 3, positive is this part here. So x less than or equal to 2, x bigger than or equal to 3. So the domain is this, minus infinity to 2
That's what I'm thinking.
and 3 to infinity. This is the domain. We get the idea for domain?
Yeah.
Why do we get cross box?
Why is it open? Because infinity isn't a real number. We can't put it into the function. It has no real value. It's actually not a member of the reals. This is true. Infinity does not belong in this set. It belongs in a different set. I believe it belongs in this set, which we haven't studied. There is a set of different... Alpha null is what you'll need to Google. Infinity belongs in a different set, a set of infinities. There's actually different levels of infinity. Yeah.
Different level of infinity.
Yeah. So it doesn't belong in the reals, it belongs in the set above it. Okay, what about this one now? Let's say hx equals x cubed. What's the domain here? All real numbers. Yep, everything. What about this one? Let's call this f again. What's the domain here?
Derivative.
No.
No.
Type in sine inverse 2. Tell me what you get.
Sine inverse 2.
Less than what?
Bigger
MAT.
than 1, less than 1. Bigger than 0, less than 1.
You don't get an answer for sine inverse 2.
No.
In fact, for this one, it is minus 1 to 1.
Oh.
Isn't it like this?
Oh, it can be.
It's because of the shape of the sine graph.
Yeah, the sign. Oh, it's minus.
Yeah?
What? What? What it can more?
Because the graph.
Graph.
Oh.
Sine x.
Sine graph.
Sine graph.
Yeah.
From
Yeah.
1 to minus
It's
1.
the same to
No, it is
No.
not actually. What is the domain of this graph, people?
this is
Everything.
Yeah.
Oh, why?
As a negative. Can negative?
This is
Of course, connected.
Of course negative, yeah.
Oh, okay.
Because this, you have two graphs, okay? This one is sine, yeah? Can you put any x? Of course you can. Any x, no problem. And you get a value for y.
Yeah.
There. This graph looks like this actually, if I can try and draw it. Oh, I can't. It's something like this. But it only has values here to here. If you look over here, like at 2, because I asked you to do sine inverse 2, you get a math error. The function, this sine inverse function, has no definition outside of minus 1 to 1. It's kind of like if you try to do square root of minus 2. The graph is not defined. The root graph looks like this, and there is nothing here. Yeah? I know it's a bit hard, but I think you're getting the idea, yeah? So that's the first half, domain. Now on to the second half, which is a bit harder, range. What do you think range is?
Which for y?
Yeah, what exactly? No, Jerry's right, it's to do with the y.
What?
It's to do with the y. What exactly is it?
Because that is through the domain for root.
Yeah, well, give me a sentence. The range.
For y.
No.
Yeah, go on, no, what do we say? The range is the
That,
set
The set of.
set of, yeah.
that obey the
Values of y.
Yeah, the y values.
That the mapping F can reach.
All the y values.
No.
Really?
Perfect.
Hmm?
The range is the set of y values that the mapping F can reach.
What is y value?
The
Will you
returned values. The values you get out. It's not really allowed. Allowed isn't quite the right word because, yeah, possible, achievable would be it. Now, trying to figure out what the range can be would be quite tricky. So just before we go on to that, just a quick graph to help you. Just to be perfectly clear.
Oh.
No, hang on, why do you need... You are the ones who gave me this definition, so why do you need to... Don't you know it? I thought... Jerry, there. Okay, so just as I continue, let me just draw a graph here. As an example. So, if I want to draw the domain, the domain is all the values on the x that I can use. In this graph, it looks like it's the whole x-axis. But, you know, maybe you might have a graph like this. It could maybe come down from minus infinity. It might break and then it might continue back up, for example. So here the domain would be all the values from minus infinity to this number, and then all the values from this number out to plus infinity. That would be the domain. What would be the range? The range is just on the y-axis. So it would be from here, up or down? Up, yeah. So these are the values here. This is not part of the range because you can never get, let's say this is a 2. You can never get less than 2 back from your mapping. So in this picture here, and maybe this is a minus 3 and this is a 3, the domain will be from minus infinity to 3 and then 3 to infinity. That would be the domain. And then what would be the range, would you say? In my picture I'll make it open. I won't include them, okay?
Minus 3, more than 3.
No, for the range?
Range is more
2 to infinity. That would be the range. So you can always find the domain and the range from the graph. If it's easy for you to draw the graph, you can do it this way. But it's not always easy to draw the graph. So let's have a look at some harder range examples. There is a technique for finding it. One technique is by using the graph. I'll give you that as a hint. I want you to try this one. Find the range of fx equals x squared minus 3x plus, plus 2. Know what to do?
Yes, but I think of the long way.
So what would you do firstly?
Find the domain.
And then find
And
one.
the domain.
What I would do is I would find just the minimum point.
Yeah.
So let me see. 2x minus 3 equals 0. So x equals 3 over 2. But I don't care about the x. I would like to know the y here, because if I knew this value of y, then I know the range is everything here. So to find the y, I need to put that in there. Let's see what we get. That would be 9 over 4 minus 9 over 4, is it? Plus 2. So the answer is 2.
2.
Oh, sorry, this is 9 over 2, thank you. So that's, what will I get here? Minus, plus 9 over 4, minus 9 over 2 is minus 9 over 4 plus 2.
Minus 1 over 4.
What is it?
Yeah, minus 1 over 4.
Thank you.
Close, more than.
Yeah, so the range would be from minus 1 over 4 to infinity then. Yeah. Now, like I said, that's one way of doing it. But let's have a look at harder ones now. Just so you know, this would be like maybe a section, like this particular one might be a section A question, but they can get harder than this, so we'll do a harder one now. Let me just have a look at the questions I gave you. So I think for the first one I wanted you to find the domain for each of these, and I think that's fine. But for the range it can get a little bit tricky. We've just done a quadratic. But what about a cubic? Let's actually...
Nice.
What is the range here, guys? It's a cubic one.
We can try.
Try. Yeah, it is. Finished. The range is done. The range is all real numbers.
What?
The range is all real numbers. Think about the graph. The graph looks like this.
The domain is all.
And the range.
Yes.
What's the range here?
Everything.
Everything. All real numbers. All real numbers, not all real numbers, all real numbers. What about here?
So now they equal 0.
All real numbers except
0.
no,
No, 0. -1.
except -1.
Yeah, -1. I mean,
Yeah. Oh, sorry.
No, it's domain.
No, I misspoke. We were doing the domain. The domain is all real numbers except
One.
-1. But what's the range though? Yeah, that's the range.
it's not really.
Yeah, it's all real numbers except 0.
0.
Why? Because it's impossible to get 0 as an answer here.
Yeah.
You can get anything you want as an answer except
0.
0. Because the only way that this could be 0 is if the bottom was...
0.
Never.
No?
Bottom one.
If the bottom was infinity. But we said earlier that it can't be infinity because that's not a real number. So at this point, it's starting to get a bit hard to do in our head, and we need a different method for finding the range. So I'm going to show you a method which I find very useful because it works for all problems. And I'll use this one as an example. Okay, so let's have a look at it. So this method here, method to find the range. Okay, so let me show you the steps. Step 1 is to rewrite it to equal 0. I'll explain that in a moment. Step 2 is pretend y is constant. And then step 3, ask when is this solvable. I'll explain with an example now. Yeah? Shall we have a look at this method? Yeah? Okay, let's have a look at this method. So let's use the example fx
Equals 1/12.
x minus 12
Plus 12.
plus 12. Okay, so we write it as an equation that equals 0. So what I mean is you rewrite it like this. First you say y equals 1/12x plus 12.
Yes.
Okay, then you say, what's that? 12yx plus 12y equals 1. But I still need to make it equal to 0. So you have 12yx plus 12y minus 1 equals 0. So I've done the first step.
No.
Now what's the second step? Yeah, so if y is a constant, then this is like 12y is a constant times x plus, and then at the back what do I have? I have a constant which is like 12y minus 1 equals 0. Okay, step 2 is done. So far so good. Step 3, ask when is this solvable? In other words, when you have this equation, when can you solve it? What type of equation is this? Linear. And when will a linear have a root? When can you solve a linear? Or when can you not, I should say. You can solve a linear. When will a linear...
It's not 0.
Yeah, but just in general, if you had a linear, when will it have a root and not have a root? This has a solution. This has a solution. This has a solution. These all have solutions. When will it not have a solution? Yeah, if it's a horizontal line. If it's horizontal. So, in other words, I can solve this provided that the m is not 0. As long as the m is not 0, can I solve it? Which means the 12y is
Not equal to
not 0, which means the y is not
not
0,
equal to
which is what we said at the start. As Jerry said, the range is all numbers except 0. Now this method works really well for hard problems, which I'm going to do. So it works nice here, but say a problem like this now. Now, this is an interesting one. Could you guess the answer here? I don't think so. It's kind of hard to see what the answer is. So let me use our method on this one now. Can I just write it over here maybe? Yeah. Well, no, I don't really have space. I'll just move it down here. Have you anyone seen this method before, or this is new?
No.
No? Okay, here's our next one. fx equals 1 over x squared minus x minus 12. And in a moment I'll make the graph so you can see it too. Okay, what's my first step? Rewrite it as an equation equal to 0. So I get y equals 1 over x squared minus x minus 12. So I get yx squared minus yx minus y12 equals 1. So just take the 1 to the left and I get minus 1 equals 0. Step 2. Y is a constant, so I would get y x squared plus minus yx plus minus 1 minus 12y equals 0. Now pretend y is a constant. What type of equation is this? Quadratic. Quadratic. When will quadratic be solvable? Step 3. When is it solvable? Yeah. When the discriminant is... No, when it's solvable. When it's solvable is if it's greater than or equal to 0. Okay? But before I continue, it's worth remembering that this only works if it is a quadratic. When will it not be a quadratic? If this part was 0.
Which one?
This one. Because then it's a linear. So the moment I say this, I also have to say and y is not 0. Because if y was 0, I would not have a quadratic to use this on. So I actually have 2 requirements. Now, that's where you have to be careful. That's the type of thing you would miss in the exam, not realizing you actually have 2 requirements for this to be solvable. The discriminant needs to be positive and the coefficient at the front needs to be not 0. So you have 2 requirements. Let's continue. B squared minus
4
AC should be positive and y should not be 0. Y squared minus minus is plus 4y plus 48 y squared should be positive. Y is not 0. 49y squared plus 4y should be positive and y should not be 0. Take out the y. 49y plus 4 should be positive and y not 0. Let's look at the graph here. What have we got? And this is actually y. 0 and minus 4 over 49. And above or below? Which do I want? I want above. So I want y to be less than or equal to minus 4 over 49 and y to be bigger than or equal to 0. But y is not to equal 0. So you have y must be less than or equal to minus 4 over 49 and we have to say y must be bigger than 0.
Mm.
So then the range is equal to minus infinity to minus 4 over 49. Open or closed?
Open. Closed.
Union.
Union. How about it?
Intersection. Open. Yes. Very interesting, isn't it? Very interesting.
What is the y-intersection among the y-axis?
Huh?
This x.
It's like the x.
Like.
Yeah, because I'm using the letter y for my quadratic instead of x.
We just use the part of y over 0.
Because it can't be 0.
Y can be minus.
Hmm?
Oh, it can be. Here's the minus part it can be. It can be minus and it can be more than 0. We can't use this part. Huh? Because we need this.
May I start to go right here because y range is here, but the one is here.
Yeah, actually the domain is quite easy to find for this. If you go back to the start, this is equal to 1 over x minus 4 x plus 3. So the domain is simply all real numbers except for minus 3 and 4. That's all the domain is. It's the range that's hard to find here. Now I said we'll have a look at the graph. So let's have a look what is happening on the graph that makes us miss part of it. Yeah? Correct. Well, this is the y-axis. Well, it's an equation of y. If you really want to get pedantic about it, I could say z equals this, and this is the z-axis. Because the x is used already in the question, so I can't use it again and onto a different letter. Let's have a look at the graph, because you might be wondering, what does the graph look like here? So what is the function? 1 over... Yeah.
Minus x minus 4.
Okay, so we said the domain is all real numbers except 2 and 3, was it? 3 and 4? Yeah, well we can see that on the graph. We can't use minus 3 and we can't use 4 because it breaks. But let's zoom out here. Hold on. Hold on. Now, what did I say the range was? From minus infinity to, which is there, and then
0.
no values are achieved here. We're missing the graph, and then from 0 to infinity. Why did I not include 0? You can see that I don't actually get 0. It is running to the axis, but it doesn't meet the axis. So this is why it's open here, but it's definitely closed here because I do reach the point here. I just do not reach it here. Yeah.
Equals infinity, it approaches, isn't it 0?
Is what 0?
No, infinity.
When it goes to infinity. Yeah, how long will that take? Yeah, it can't go to infinity though, because I said infinity is not a number you can use. So it never actually is allowed to say when it is infinity, it's 0. So because it's never infinity, it's never 0. What's the problem? Can x equal infinity? No. So if x can't equal infinity, can y equal 0? No. So it's open at 0, can't be reached. No, it's open at 0, cannot reach 0. Because the reason is it cannot reach infinity on the x-axis. No, not even in its wildest dreams can it reach infinity. I'm afraid it will always be close to, but never at infinity, and that means on the y-axis it will be forever close to, but never at 0. Very, very sad. Okay, let's have a look here now at so for this lesson now, we're practicing domain and range. The example I just did here, this would be the hardest it could be on the exam. Okay, if you want to go totally nuts and try a really hard one, this is a beautiful one here. Quadratic over a quadratic makes a very interesting problem here. But for exam purposes, sometimes I see e and logs and roots, but I've never seen them do a quadratic over quadratic. It's a bit too hard, okay? So can you try these for a couple of minutes and then we'll go on to the next lesson.